Well, I should tell you how the two of these lectures or talks came about. At one time I was trying to recruit, and I was recruiting at Northwestern, and Herman Pines, one of the old fathers of catalytic research, said to me, he said, you know, the trouble with catalyst research is not very exciting. He said, you know, it's not atomic physics or nuclear reactors or solar energy. And he said, it's pretty hard to get people interested in catalysis. I said, Herman, what do you mean? It's one of the most exciting fields in science, I think. It incorporates a lot of good science, a lot of intuition, and a lot of alchemy, and in addition, a lot of luck. So I decided that maybe I should try to put together something that would encompass the what I felt was the excitement of catalysis. And I've always been interested in those scientists who developed a lot of these products and the personalities behind them. And I have a large book back in my office that actually details the lives of a lot of these people. And I'm just going to try to highlight them for you today. But I think it's important to get a feel for the personalities behind these catalysts. They're all very interesting people. I've had the pleasure of meeting some of the later pioneers, and they not only are good scientists, but they are wonderful people in many ways. And I also thought that catalysis was, I decided to try to get a catchy name, you know, for it, so I called it the Romance of Catalysis. And I used to also incorporate some romantic figures in my speech from Paris, but I decided I'd better not do that today. But, you know, catalysis goes back, way back. The Romance of Catalysis connected with a jug of wine, loaf of bread, and thou. One of the earliest catalytic achievements of man, of course, is the production of alcohol. And it's an interesting organism that produces that. Also, one of the earliest, come on up, Dick. One of the earliest examples of a catalyst in a poison is the other organism, the Acetobacter, the organism which, if it contaminates your wine, turns your wine into vinegar. And so we have examples of catalysis being with man from almost the beginning. I think that gives it a romantic character. There are interesting examples of early poisons connected with that. One of the theories of the decline of the Roman Empire is postulated that what really happened to the Romans was that they kept their wine in leaden vessels, and the peasants couldn't afford leaden vessels. Lead was scarce and costly, and the solubility of lead in alcohol is such that a small amount accumulated therein, and the Romans drinking wine all the time, they gradually lead poisoned themselves, and particularly the fertility. So we have some very early examples of not only catalysts and catalysts going astray, but examples of poisons as well. By the way, we decided to record this if we could. It's an experiment too. I don't know if it'll work, but we thought for later on, if I can't make it or someone else can do it better, perhaps we can develop this into a series which be canned, and anyone that wants to be brought up to date on catalysis can view these taped videotapes. Well, going on, later on in about the 7th century, the Arabs were quite capable in science, and of course they invented or discovered that you could make esters and ethers from alcohols with sulfuric acid, and so that was an example of another early use of catalysis. I'm going to jump ahead to try to sort of catch your attention and then go back and pick up some of these early people. But I want to take an example of the glamour of catalysis by citing you the case of the platinum reforming catalyst. This is a very intriguing story in its own right, and it has a great historical background. Most of you are familiar with the fact that there is a platinum reforming catalyst. Later on in this series we'll talk in detail about platinum reforming, all the mechanisms involved. But the discovery that a small amount of platinum, very expensive metal, and today it's $800 and some an ounce, was a great discovery. And it came about as a result of a need for high-octane gasoline after World War II. Prior to that time, before World War II, there was, of course, a small demand for high-octane gasoline, and they had a lead additive that would do the job. But after the war, the compression ratios were increased. The welcome, PAD. And those in the know knew that the way to get a high-octane gasoline, and therefore a high-compression engine, and therefore a higher performance engine, knew that aromatics were highly desirable. So a young man by the name of Val Hensel, working at UOP laboratories in Chicago, had been trained under Vladimir Padiev, the great Russian catalytic scientist who later came to the United States, and I'll tell you a little bit about him. They started to experiment with putting platinum on alumina. They knew that was a good dehydrogenation catalyst. And he started passing naphtha over this platinum on alumina catalyst. And lo and behold, he began to get a high octane number. But that was only the beginning, because the first thing that he had to overcome, as all of you know, when you make a great discovery like that, it was the comment, how the devil do you expect to make a process go that involves a precious metal like platinum? You must be out of your mind. Well, Val pursued, and UOP persisted, and out of that did come the platinum reforming catalyst. A simple thing, 0.6% platinum on alumina, but literally billions and billions of dollars were spent in developing that catalyst, because it isn't just platinum on alumina. It's a very complicated alumina structure, has a very complicated pore structure, and how you put the platinum on and how you treat it and how you get the acidity that you need for the dual types of reactions. All these took a long time to evolve, and is still evolving, some 33 years later. Well, I thought I'd start by at least introducing you to some of the individuals who were responsible. Would someone turn the, I think Larry was going to be back there. First of all, I just wanted to present some of the catalysts, various colors and shapes, to get you a little bit enthused about the aesthetic qualities of catalysts and the tremendous cost that's usually involved in developing any one of these catalysts, and there are many. And I only wish that I could go back and study the personalities of each of the developers of every one of these catalysts. As you know, I have a collection of about 130 industrial catalysts in my office. These are just some more. And these are the early samples of platinum reforming catalyst, and each one of them has a very interesting story connected with it. This is the first platinum reforming catalyst of UOP Val Hensel. It's a bead formed catalyst, and it has anywhere from 0.3 to 0.6% platinum. Come on in, John. And we get Frank out of the way, we'll go on with this catalyst is another catalyst that was developed almost simultaneously, and it's a silica alumina catalyst. By the way, this platinum on alumina catalyst also has about 1% fluoride on it, an attempt to promote the acidity of the reaction, and later on we'll get into carbonium ion reaction mechanisms and dual reaction mechanisms and so forth. But Val Hensel got his acidity with hydrogen fluoride. Frank Schiappetta, starting almost the same time, and those of you who are members of the Catalyst Club will recognize the Schiappetta lectures, the memorial lectures that are given once a year at the clubs. And Frank, what he did was put platinum on silica alumina. And those of you involved in cracking catalysts know that silica alumina has an acidity, not very good compared to the modern zeolite silica aluminas, but it has quite a bit of acidity, and it was too strong an acidity, and so Frank got his acidity by steaming down to a very low level of acidity, a very low surface area. And it was a fairly good catalyst too, and it was used for quite some time. Not by everybody, but there were a number of units using that material. Then my introduction to platinum reforming catalysts was at Sinclair Laboratories in Chicago, where I had the good experience of learning all about catalysis by the late John Teeter, who was, maybe I should give a lecture about him sometime. He was quite a guy. He was sort of the John Wayne of the catalyst research industry. Anyhow, John's great contributions not only were that his team developed a new alumina, and by the way, there was a new alumina discovered here that had never been known before, but he also was daring enough to try extrusion. At that time, nobody would let you put an extruded catalyst into a unit. It had to be a pelleted catalyst. And John knew he could make a cheaper catalyst if he extruded it. We also learned something else at that time, and that was that the reaction rate and the rate of coking was dependent on particle size. And so John said, I'm going to make a 16th-inch catalyst, and that was horrors double, because every engineer knew that the pressure drop would be excessive and that it would be very difficult to operate with an extruded and a small diameter catalyst. Nevertheless, he persisted, and that catalyst went into operation, and some 30 years later, that catalyst is still being used in many places around the world. It's the famous RD150 catalyst. And I put these on red velvet to give them these have platinum in them, and they do have a value closely associated with it. The work in precious metal catalysis goes back to before the turn of the century, when high pressure catalysis and working with precious metals was pioneered by both Vladimir Padiev, and I'll tell you a little bit more about him, and Paul Sabatier of France. Now, Padiev was a very unusual guy, a very handsome guy, very debonair. He was a military general in the Russian army, and he was in the artillery. By the way, there's some more seats up here. You want to come up here? Come on up, Sam. He became curious about what was going on in cannon. What kind of chemistry was going on in the cannon? So he began to bottle up cannons and carry out reactions. And he really pioneered really high pressure catalysis. And he also was very fond of hydrogenation work, and so his bomb work with various things and with hydrogen, he began to focus on nickel and platinum and some of these other things, and found that they would hydrogenate various aromatic molecules and so forth. He did a lot of work. The interesting thing about him was that he was in the artillery and he had to travel, and he carried his laboratory with him. Whenever he got into some location, he would set up and do research, and I consider that a persistent characteristic of good catalyst researchers. He got to working so he could work up to 450 atmospheres, and that became key to later developments that occurred in Germany, which I'll tell you about shortly. I think some other interesting things about him. He was chairman of the chemical committee of the USSR after World War I, and the interesting thing was he never joined the Communist Party. He was so good that they couldn't do without him even if he wasn't a communist. And he founded and directed the Institute of High Pressure Research in Leningrad in 1927. Well, he was not happy with the communist regime in Russia, and also he had a suspicion that Joe Stalin didn't like generals. And so on the pretext of a tour of technology in Europe, he escaped into Germany, where the famous Gus Egloff, a vice president for research at UOP, was busy trying to put a research team together in the late 20s and the early 30s. And Gus Egloff was a very persistent cuss. I had the pleasure of seeing Gus just before he died. A very dynamic little guy, little mustache. And he talked Padiev into coming to the United States, and he talked Northwestern University to making him a professor. Some of the requirements for immigration were rather strict at that time. This was one way to accomplish it. Well, what a blessing it was for the United States, because he became a citizen in 1936, but he went on to make great contributions in catalysis, which I'll talk about, many of them which were very critical to the war effort in World War II. And also the teams that he put together there also went on to become very famous people in their own right. And he became a rallying point for other people in difficulty. For example, Hans Tropsch from Germany, of the Fischer-Tropsch fame, came to Evanston to join Padiev, and many other people, same way. At the same time, he founded the Padiev high-pressure laboratories with some of the royalties that he accumulated for his patents at Northwestern. So he's quite a guy. He was, I was at Northwestern when he was still alive. He was 80-some years old. He had shrunken a little bit, but he still had a grand imperial bow. Every time you met him in the hall, he would go through a grand curtsy or whatever. And he was in his laboratory working until, in fact, the day of his death, still teaching students, still carrying out high-pressure reactions. I don't know if you can see this, but this is the famous Paul Sabatier, who also pioneered in precious metal and nickel catalysis prior to World War I and in the turn of the century. He was born in 1854 and died in 1941, so he's a contemporary in many ways. I have a very nice picture that was given to me by Professor Burwell at Northwestern showing Padiev and Sabatier shaking hands, and that's quite an interesting picture. Well, Sabatier was a Nobel Prize winner for his work with a Grignard in 1912, and he too, of course, as I mentioned, was famous for his work in hydrogenation with transition metals, and professor of chemistry at the University of Toulouse. Well, the precious metal story goes on, kind of on and on and on, but it never turns into a tremendous field, except for the field of nickel hydrogenation of oils, which occurred early in this century. But this is a picture of Val Hensel, who since has won the President's Medal for his work in science. His contribution in platinum chemistry is one of his great contributions. He's also one of the spearheads of the formation of the Catalyst Society. Val was here for our opening of the Tri-State Catalyst Club, our first meeting several years ago, and those of you had a chance to hear him. He still has his vigor and still his enthusiasm. And I talked to him the other day, and he is now working at the University of Massachusetts 1 week a month and trying to help them assemble a catalytic research facility there. Well, Val had the good fortune of training under Egloff. And Padiev. He was one of Padiev's first student. And he was also a member of the team that toured Germany after World War II. And of course, I think that he was a very young man at that time, about 28 or 30. It was quite an honor to be chosen as one of the member of that team. And I think he got a lot of ideas at that time too. And as I mentioned, he received the National Medal of Science in 1973 for his work in platinum chemistry. And finally, here's the other pioneer in this platinum reforming, a good friend, Dr. Frank Ciapetta. He met an untimely death in Argentina in 1969, I believe it was. He had a heart attack in the hot summer sun in Argentina. Frank was an enthusiast for catalysis, did a lot of lecturing, and was responsible for the enthusiasm which led to that Catalyst Research Center in Delaware. and also was a great builder of the Catalyst Society. The early 1900s, of course, became world famous for their work in catalysis. They really learned how to exploit catalysis, but still it was always captured within a small group. And after World War II, with the introduction of platinum, there was formed catalyst clubs in Chicago and Philadelphia, and later on other sites. We're the youngest one. There was 12 of them now. People began to exchange ideas, and all the petroleum companies jumped into this platinum research. Every one of them, either to come up with their own catalyst or to learn enough about petroleum processing with these catalysts so that they could operate at maximum efficiency. And as a result, these really sophisticated laboratories began to develop in all the big petroleum laboratories in the country. I know when I speak of the facilities we had in 1950 in Harvey, Illinois, at Sinclair, it's hard for people to believe at this day and age that we had so much awareness. We had all the tools that you have in your laboratory here today, and probably some besides that. And so suddenly this tremendous dedication, and the society sprung up, and there were meetings, there was exchange, and people would go to these meetings and they'd try to find out what each other was doing, and a little intelligence gathering. But out of it came some remarkable things, I think. I think there was a tremendous jump in the advances in catalyst testing techniques. Much more sophisticated techniques were developed, and microreactors and so forth all came on. An improved understanding of catalyst regeneration. The platinum catalysts had the one undesirable characteristic. If you use them long enough, as Dick knows, they coke up, and you either have to throw it away, and someone said, well, why don't we burn the coke off and do it over again? So they began to regenerate these platinum catalysts, and they began to study regeneration very intensively. And we studied platinum, what happened in regeneration and reduction, and the mobility of the platinum, and you get it down into clusters and you could redisperse it and it'd come back, and the alumina would age. And so we developed regeneration, rejuvenation as concepts. I think there was a tremendous acceleration in use of research tools because everyone was trying to find out what was going on with platinum. How big was the crystallite size? What was the pore structure? What was the reaction mechanism? The dual site reaction mechanism unfolded at that time. Alumina chemistry was not just Al2O3, but alumina, there must be as many as 1 million different aluminas. You give me, you tell me you've got an alumina, and I'll tell you how to make 1 million different ones. That's because there are 5 different alumina hydrates, and there are different crystallite sizes. You can put them together in any ratio. And with these combinations, you control surface area, acidity, porosity, pore distribution, and so forth. And also the support upon which the precious metal or other active ingredients are supported. So great strides were made here. The active crystallite size became very important, and the effect of the interaction with the support. And later on we'll talk about that in much greater detail. I only mention it here in passing. Precious metal catalysis got a big boost. I know I was involved in the very early days. We said, I wonder if platinum's good, what happens to iridium, rhodium, ruthenium, osmium, and nickel, cobalt, and so forth. So all these precious metals, and what happens if you put the two together? And while the dual, the bimetallics are now new, at that time they were already envisioned. And when we get into reforming, we'll talk about the bimetallics and the trimetallics. There are a lot of new techniques in catalyst pretreatment and regeneration, rejuvenation. In regeneration, you have to watch your oxygen partial pressure. In regeneration, you also have to watch when you reduce the catalyst afterwards, how you do it. You have to watch out for sulfur, other contaminants. You have to watch out for high temperature waves through the bed. So a lot of things here that really got a lot of attention at that time. And everybody was involved. Every petroleum company, 15 petroleum companies, let's say, everybody had reformers. Everybody had scientists, and they worked very closely together. Well, certainly the work we did at Sinclair made a major impact on particle size, and later on we talk about hydrotreating. I'll show you how that went from reforming to hydrotreating, and even to H-coal, and it's still, and it also led to the fluid cracking catalyst, and also the use of hydrocarbon reaction mechanisms to probe the catalyst. While that had been pioneered before then, it became a very intensive activity. I know that I spent a lot of time in that area, and understanding the mechanisms became very important in the final development of new catalysts. Well, now that I hope I've caught your interest at least with something that you can relate to, I'd like to go back and just spend a little time giving you some background on catalysis. First of all, the word kata is kind of a Greek interpretation of meaning wholly down or downward, and it relates to the vision that the molecule has to go down on the surface to be changed, although we have homogeneous catalysis, of course, too now. And lysis, to loosen or disintegrate. So the idea of catalysis, as John Jacob Berzelius visualized it, was that the molecule settled on this solid and was all shaken up, in which it was, and reorganized and then desorbed. And the catalyst was not affected, but only the reactants in the product. So Berzelius defined it, and by the way, he was born in 1779, so he's one of the early real catalyst workers. And he lived until 1848. And he's also one that originated the present-day symbols of the elements and the use of formula, so he made a lot of contributions. But his definition of a catalyst is a substance which by its mere presence evokes chemical reactions that would not otherwise take place. And I think that's a pretty good definition. And here's old John Jacob Berzelius with all his medals, and you can see catalyzers were given great honor in those days. Wilhelm Ostwald was more of a physical chemist, and he began to realize that not only did the catalyst bring about these changes, but it also affected the rate. And so it affects the rate forward and affects the rate backwards. But it established an equilibrium between two species and not with every potential species. And so he defined it as a substance that changes the velocity of a chemical reaction without itself appearing in the end products. And it's sort of like the minister at a marriage ceremony. The couple come in, they're two individuals. The minister performs the ceremony. The couple go out now as one, man and wife. The minister goes on his way. Whether the couple live happily ever after or not, one doesn't know, but the minister is not affected. It's also sort of like putting a nickel or dime, I guess today I have to say dime, the telephone to get the operator and get a call. And when you name the operator, you get your dime back. So a dime is sort of like a catalyst. There's Wilhelm Ostwald. He's almost a contemporary, at least for some of us. He was born in 1853 and lived until 1932. And one of his great contributions was he developed the catalytic process for oxidation of ammonia to make nitric acid. And that was the beginning, really, of the German chemical industry, because, as you'll see later, they learned how to make ammonia. They could also make nitric acid. They could make nitrates, explosives. They could make ammonia for fertilizer. And they could make liquid hydrocarbons from coal, and so they had almost an independent society. Well, Ostwald received the Nobel Prize in Chemistry in 1909 for his work in catalysts. There have been a number of catalyst people who have received the Nobel Prize, at least in the earlier days. Well, I'd like to go back and kind of pick up, we talked about the definition, I'd like to go back and pick up some of these other early pioneers who I think are important to give you a good feeling for where this all came from. And one of the early great scientists was Antoine Lavoisier, the great Frenchman. and he was the one that was concerned with the reaction rates, atomic weights, and using nomenclature for acids and bases. His work is considered one of the classics in chemistry even today. Unfortunately, his career was shortened dramatically by the guillotine in 1794, and it was tragic. And Lagrange said, and I quote, "A moment was all that was necessary to strike off his head, and probably 100 years will not be sufficient to produce another like him." Lavoisier was also a believer in equal opportunity. His wife was his laboratory assistant. And by the way, here you see him performing some early experiments on oxidation and breathing. And he was one of the early ones to understand that man did in fact live upon the air that they breathe. And while it sounds pretty obvious today, it was a great step forward at that time. This is somewhat of a more romantic picture of the two, to get a little romance into this lecture. She was a great assistant to him, and they were very fond of one another and worked closely, and he had great joy in this work. Well, let's look at just some of the early developments in chemistry. The acid hydrolysis of starch in 1781, that was a very interesting development. Dehydrogenation of alcohols by metals to make olefins, very interesting early discovery. And using metals. Dehydration of alcohol with clay. Catalytic combustion with metals. I think that eventually led to the old Welsbach mantle for getting high intensity illumination. And decomposition of ammonia and hydrogen peroxide, which gave them a better understanding of what ammonia was. Then in 1825, Michael Faraday, the great British English scientist, was the first one to actually make ammonia. And of course, this has been one of the major contributions to civilization, in the sense that once man knew how to make ammonia synthetically, he was no longer dependent on plants and so forth for ammonia. And now the population was not dependent on the ability of the land to produce food, because you could with ammonia, you could step up the productivity of the land, and as a result you could grow more grain, you could grow more cattle, livestock, and you could support more people, and therefore the population explosion started not at this time, but about almost 100 years later with this very reaction. But Faraday was the first one to do that, and Berzelius with his definition, 1836. This is the great Sir Humphrey Davy, brilliant scientist, a rather short career. He died rather early, but among his other things was laughing gas, and anesthetics for dentistry. He was a lecturer in London, and did many great things in a very short career. He also said that one of his great discoveries was Michael Faraday, who some people still consider one of the great scientists of all time. And this is young Michael Faraday. As you know, he was not only great in chemistry, but in magnetism, the electric motor, dynamo, magnetism, all these things also are related to Michael Faraday's work. Now, his laboratory was in the basement of the Royal Institute in London, and if you think things are tough here, just think what he accomplished with that laboratory. Every time things are tough here, a little crowd, maybe I should pull this slide out. And but this is where he worked, and what more can you say? It was evidence of a great mind at work. I think something's happened. No, I'm sorry. That is now Mitscherlich, who was one of the individuals who learn more about really contact catalysis. He really began to understand, although Ostwald had talked about reaction rates, Mr. Lick was really ahead of Ostwald in making use of the concepts of speeding up reactions. And he really began to understand that it took a surface to do the job, although Berzelius had spoken of this contact phenomenon. Well, then the era of industrial catalysis began to occur about this time in 1868. First industrial reaction was the Deacon process. It was designed to make chlorine from hydrochloric acid. And the Winkler reaction for oxidation of SO2 to SO3 with platinum, that for the first time really began to bring platinum out, out in the spotlight. At the same time, they learned you could go from methanol to formaldehyde, and that's an interesting reaction, very much used today. The Claus reaction, we're using it every day. We have Claus reactors in our refineries. At that time, it was H2S with air. Now it's actually H2S with SO2. Actually, you do convert some of the H2S to SO2, and then you react the H2S with the SO2 to give you sulfur. Then we see the period when firms begin to get involved. First we have just curiosity and scientific curiosity. Then we have developing of processes by individuals. And finally we have companies beginning to see that if they apply this technology in a logical way, that in fact it can be a very profitable endeavor for a company. So this is the beginning of, this was somewhat after Edison first built his first industrial laboratory in New Jersey. And I think the Germans took a page out of Edison's book and started on their own. So they began to make a number of introductions, and the great Bosch firm, which remained powerful until end of World War II, really began to show its muscle at that time. Phthalic acid made at that time. This was a separate one. They showed you could, besides platinum, you could use iron oxide, and today we use vanadium. Now, in 1902, the catalytic hydrogenation of oils and fats to make margarine first appeared on the scene, and this process eventually led to a great understanding and the involvement of the nickel catalyst for hydrogenation. At the time this was done, hydrogen was made by electrolysis, and so it wasn't surprising that electrical engineers were involved in this work. And at the end of this whole lecture, I'll tell you about an electrical engineer who became one of the most famous catalytic chemists of all time because he got interested in this reaction. And at this time, Ostwald also really came out with his oxidation process. Another minor one was catalytic production of hydrazine. Now, in 1908, this is when it really becomes a really big business, when Haber discovered that he could make ammonia with an iron catalyst. And, of course, as I say, that was very important to the Germans, and I think they gave them an overly optimistic opinion of their own capabilities. Of course, the Germans did not start World War I. It was a Hungarian empire that really triggered off World War I, but the Germans apparently were well prepared for it and joined in very quickly thereafter. But it was 1908 when this occurred, and the team of Haber and Bosch, Karl Bosch, and I'll show you his picture. He's a stern, tough-looking old German, but boy, he sure knew how to design high-pressure equipment. You know, if you see some of the equipment that the Germans built in World War II, for example, it's hard to believe that they could build all this high-pressure equipment while the bombs were falling, when we're taking, 4 or 5 years to build a much smaller unit today under peaceful conditions. Of course, people were highly motivated, and that has a bearing on it too. Yeah, we have reverse motivation today. Then, of course, catalytic production of hydrogen from carbon dioxide and water. And then carbon monoxide reduction under pressure to different organic compounds, which led to the Fischer-Tropsch process. But this was a big breakthrough here, with a way to make hydrogen in large quantities cheaply from coal, for example. And with nitrogen, you then had all you needed to really be independent in making ammonia. So this was a very, very busy time in Germany. You can see that. And this is Fritz Haber. He's quite a precise-looking individual. He was director of the Kaiser Wilhelm Institute, and for his work in he won the Nobel Prize in 1919 for his work in synthesis of ammonia. And I've already talked about the importance of ammonia. And this tough-looking cookie is Carl Bosch. And the thing that's interesting about Carl Bosch, by the way, he lived until 1940, and Fritz Haber lived until 1934, so you see it isn't that long ago that these people were still actively doing research. When you try to visualize building all this high-pressure equipment today with all the modern tools we have, we just wonder how they were able to do it. Well, we'll go on to catalytic oxidation with others besides platinum, although it's still platinum today, really. Catalytic oxidation of hydrogen sulfide, not a great thing, but carbon monoxide oxidation, these were not great developments in this period. Methanol production, of course, was, and that's all the rage today. 60 years later, it's become a very attractive reaction. But the real progress started to accelerate just before World War II. It was almost as though the Germans were getting ready for a war, and almost as though the Americans were anticipating that they might be in war. And Burgess invented the coal hydrogenation process in 1926, actually even earlier he was working on it. And as soon as our good friends Exxon, it was Standard Oil of New Jersey at that time, learned of it, they made an agreement with Bosch to work on the bottom of the barrel. At that time, there was a great threat of a shortage of oil. The world was running out of oil in 1928, and so everybody thought, well, let's convert the bottom of the barrel. It sounds familiar, doesn't it? And Exxon made an agreement with Bosch. Bosch would work on coal, and Exxon would work on hydrogenation of resid. They brought the know-how of the United States. They built a reacting system in Baton Rouge, Louisiana. They built a complete plant to make hydrogen. They even built a complete plant to make all the catalysts that are involved. And there are a number of catalysts involved in making hydrogen to supply this process. You have to have a steam reforming catalyst. First of all, you have to move sulfur. You have to have desulfurization catalyst. If you have a catalyst take sulfur out, you need a reforming catalyst. And after you've got steam and carbon monoxide, you need a gas shift catalyst to convert the carbon monoxide to carbon dioxide and more hydrogen. And so it goes. To make hydrogen required making a lot of catalysts in addition to the catalysts used for residual hydrogenation. And it's really the forerunner of the H-oil process and the H-coal process today, and the Exxon donor. And if you think Exxon is new at coal hydrogenation and so forth, you have to realize that they've been looking at this process for 50 years. In 1930, a lot of oil was discovered in Oklahoma and Texas, and the need for this operation diminished. And for the next 10 years, Exxon used that plant to study the hydrogenation of lube oil. Does that sound familiar to you? All of us are still looking at lube oil hydrogenation today. At the same time, the team of Fischer and Tropsch in Germany discovered by accident, really, that if they passed carbon monoxide and hydrogen over certain catalysts, they would get a hydrocarbon. Everybody knew you're supposed to get methane, but They didn't. They got waxies and high molecular weight hydrocarbons. And of course, this was exciting because now you had a potential of making liquid hydrocarbon fuels for automobiles, for aircraft. They didn't have jet aircraft till near the end of the war, but you could make fuels for a war machine. And about the same time, Sabatier discovered that he could take propylene from thermal cracking operations, which were carried on in the United States, and condense it, and he would get C6 and C7, C8 olefins from C3, C4 olefins. He found if you hydrogenate it, you could make isooctane. If you took one methyl off by methyl clipping with nickel, you'd get tryptane. And so the high-octane fuels that ran our war machine, World War II, came from that work. And then in 1936, the great Eugene Hoodry introduced catalytic cracking to the world. And if I have time, I'll just talk a little bit about Hoodry. He was another very fascinating guy. And then in 1937, 1940, alkylation, reforming, isomerization, synthetic rubber dehydrogenation, among others. And suddenly, in preparation for war, or whether it was a coincidence, which enabled war, I don't know, but all these processes started to come on fast. And here's Burgess, Nobel Prize winner, and quite a guy in his own right. He discipline of the high pressure technology in Germany. And here's a scene assembly of our H-coal operation here in Catlettsburg, so we have a direct connection with that. And this is Franz Fischer. He was born in 1877, died in 1947, and began his work on the carbonization of coal. And it was his work together with Hans Tropsch that led to the Fischer-Tropsch process. Now, Hans Tropsch was a little more wise. He was a Czechoslovakian, and he managed to escape to the United States in 1935. He came to the United States and began working with Egloff, and he contributed to many developments too, which Sabatier had pioneered. This is just another picture of Sabatier in his laboratory. And this is how I looked in later years in Northwestern. This was taken about 1953, and still a grand old man. Here's a wonderful character, Eugene Hoodry. He was born in France in 1892 and died about 16, 17 years ago here in the United States. He was an active, he was very wealthy. He was a gallant individual, and he received the Croix de Guerre and Legion of Honor for his gallantry in combat in World War I. He was of that fast-moving generation, the Roaring Twenties, and he, like many others, had a powerful racing car, and it wasn't powerful enough for him. He was a chemical engineer, and he was determined to develop more powerful gasolines. And so he set up a laboratory, and he began to pass oils over these clays and everything he'd get his hands on at high temperature. And he would get a liquid product. At that time, thermal cracking was the way you converted heavy oils into gasoline and so forth. You got a low octane number. You know, thermal gasolines give you a 70 octane number. And so he set up this laboratory, he'd pass stuff over it, and he'd get the product, and he'd distill it all and take a gasoline cut. And, you know, he had to make quite a bit to take care of an automobile. He put in the gas tank, and he had a hill. And he'd start at the bottom, and if any of you recall some of these old cars, like the Model T, he'd start up a hill, it'd die on you about halfway up. And he'd get in his car and go charging up the hill, and every time he got a little higher out there, he'd make a mark, and he had a little better product. A pretty crude research octane number, Mike, but finally one day he was processing some acid-treated montmorillonite clay, and he put it in the reactor, and he got this conversion, he got this product, put it in the car, boom, up the hill he went, and eureka, boy, that car went right on to the top. And he knew that he had hit upon something. The only trouble was that, first of all, no one paid much attention to him, and the other was that after about a few minutes operation, he had so much coke, the reaction was shut down. And so he spent a number of years, that didn't dismay him, and he would lay down coke, burn it off, run the reaction, and he was doing fine. So he came to the United States in 1931. He figured he couldn't exploit it in France, so he'd exploit it in the U.S. In the U.S. He founded the Hood Process Corporation. He got some support from Sun Oil, a little bit from Mobil Oil, and he started doing more serious work. And finally, he came up with a process that was pretty crude at that time. You had these chambers of catalyst, and you could either have cycling in there, or someone even invented a rotating reactor. You'd pass oil for a little while, then you'd purge with steam, then you regenerate, and then you'd come back with oil. And that first process was built and completed in 1938 in New Jersey. And it was, in a way, it was a blessing that it came at that time. Well, Exxon heard of it, and they plunged into it, and eventually they came up with a fluid bed process. Mobil plunged into it, and they said that there has to be a better way than this rotating or cycling. So they came up with a moving bed pellets. And so to this day, you have the TCC process, although it's rapidly disappearing because it's not nearly as efficient or selective, and the fluid cracking catalyst process. But it was Eugene Hoodry that made this discovery, and he also made during World War II, he invented the process for making butadiene, which was the key to synthetic rubber. He also started pioneering oxidation catalysts for auto exhaust in 1948, so he's the granddaddy of the auto exhaust catalyst as well. And he had another area which I got involved in a way later on, in a much more intensive way perhaps, but he was also interested in aging research. He had a rather elementary concept. He said, if a catalyst ages, I lay down coke. If I burn the coke off, I got to do catalyst. Okay. I use oxygen, I eat food, I lay down carbon. Maybe if I increase the oxygen partial pressure in my environment, I'll prevent the coke from forming and I'll live longer. So he experimented with that, and he used to keep a tent of high pressure oxygen that he slept in overnight. Unfortunately, it didn't extend his life very much, although he did live to be 72, and it was vigorous. And his financial assistance to the first International Congress on Catalysis in 1956 led to that first Congress, and so he is really the guy that gave the seed money that get the International Congresses going. Well, for those of you, and we'll talk about catalytic cracking in much detail, but just tonight I just wanted to show you what catalytic cracking does. If you take a molecule like cetane or some other one, this happens to be nonane or decane, it has a very low octane number. There's no branching. A normal paraffin has a very low octane number. Normal heptane has 0 octane number. Isooctane, highly branched, has 100 octane number. In thermal cracking, you chop this 2 at a time. You make ethylene and a shorter chain. And so you get no benefit. And so thermal cracking is not a very attractive way to go if you want to get a high octane and a good selectivity. But with catalytic cracking, you get a carbonium ion, and we'll talk about that later. The molecule reorganizes. You get a tertiary carbon here. It splits off, leaving another fragment which isomerizes, and you get isobutane, which can be combined with isobutylene for high-octane gasoline, plus high-octane components. The C5, 6, 7 aromatics, olefins, and paraffins all have high-octane numbers. This is a fluid cracking catalyst. This is magnified many times, 1,000 times or more. And what it is, little microspheres. And these microspheres, when passed together, flow like water, and gases can move them, and you can move them from one reactor to another, and they seek an equal level, as you can see. And that is the great process, and that's the workhorse of the petroleum industry today. And of course, the one that we're vitally concerned with the RCC process. Well, I'll just quickly go through the developments since then. It was learned in the early 40s that if you passed normal heptane over molybdenum catalyst or chromium catalyst, that you could also make aromatics. That was the original dehydrocyclization reaction to toluene. And 41 to 46 is when alkylation of isobutane with an olefin to give high-octane gasoline came on. At the same time, they learned that if you isomerize normal pentane, you can greatly increase the octane number for pentane and naphthas. I mentioned butadiene. Isomerization of butane, if you have normal butane and you want to make isooctane, you first must get isobutane and then react it with an olefin to give you the isooctane. And the catalytic cracking of residuals, even back in 1948, was begun. Not very successfully, but goes back to that time. And then reforming 1949, which I've already spoken of. When this thing accelerates, as I indicated, Mobil discovered that instead of using bucket elevators to circulate catalysts, they could use an airlift. And so these processes were developed. But today they're pretty much passé. There are a number of these units still in operation, but they're really costly to operate. We found that we could make benzene and aromatics from naphtha in the reforming process, and so it greatly increased the availability of benzene in the United States. About this time, the great activity in hydrodesulfurization really began in earnest. The so-called blue cobalt moly catalysts, that, of course, has become another great workhorse of the petroleum industry. I've talked about alkylation for motor gasoline. Prior to that, it had been for aviation gasoline. They were able to simplify the process, reduce the cost. About this time, 1955, too, they discovered, although this has not yet turned out to be a great application development, but they found that they could use urea to form a clathrate compound around normal paraffin and separate out wax. And that's kind of an interesting thing because it began to get people thinking about molecular sieves and molecular size and that sort of thing. 1959, hydrocracking appeared on the scene. This is a combination of hydrogen processing and catalytic cracking. You do it under high pressure. Catalyst doesn't age. You get isomerization, all the reactions associated with catalytic cracking. Unfortunately, it's a very expensive process. It was anticipated that hydrocracking would replace catalytic cracking by 1970 or 75, but the emergence of the sieve catalyst in catalytic cracking has completely reversed that trend. In 1962, I don't know what happened to sieve. Zeolite catalyst, okay. 1962 was discovered that instead of having a homogeneous bed, if you had a riser bed, you could get better selective cracking. And that came at the same time that the zeolite catalysts, which are extremely active, were introduced. As you recall, we had Charlie Plank here a year ago talking. He was the great discoverer of the zeolite catalysts, which have completely revolutionized the petroleum industry and promises to continue revolutionizing it. And we'll talk about that much later in considerable detail as we get into the details of zeolite chemistry and catalysis. But this was a invention of hardware because you're dealing with a very active catalyst that can promote explosions with hydrogen on one side and regeneration on the other. It took a lot of courage really to come up with that process, and it has a special catalyst going with it. And then in 1973 they began to discover that if you want high octane number, you could get it by running your cat crackers at higher temperature. So that took new construction of cat cracking units and also catalysts that could take it. And we're still involved in developing catalysts that are even more rugged than the ones that were. This is just a picture of the desulfurization catalyst. I just want to say something about it. This young man born in Kentucky, he was very poor circumstances. He was able to get to the University of Kentucky and work his way through electrical engineering. And by the way, his picture is on the wall now at the University of Kentucky in the engineering school, just as a graduate with all the others, no special thing, but you can see it there, picture of graduates. And he was hired to work on fatty acids and oil hydrogenation, and because of his background in electrical engineering. And he he became enamored with the nickel catalysts that were available at that time, and he was familiar with alloys, and he knew that a nickel silicon alloy could be made, and he proposed that if he could make that alloy and leach out the silicon, he ought to have a very high surface area catalyst. Well, he did. I was down in Chattanooga, saw the house where he had worked. He worked in his kitchen doing this, and lo and behold, the catalyst worked, and later on he began to try other alloys, and he tried aluminum, and that turned out even better. And that catalyst became so popular. It's the Rainy nickel catalyst, and it became so popular that you know, it was everybody's brother wants some. They'd write into Murray Rainey, say, "Hey, would you make me some of that Rainy nickel catalyst?" And he'd make it. He made it for everybody, and he never charged very much for it. Never gained very much for it until he sold the company to W.R. Grace about 1963, I guess. But he always did it. He'd make you some, he'd sell it to you, but he never made a profit. But that catalyst was used so much that every organic chemist, every laboratory, every university, first thing they did, they want to teach something, or they're trying something new, or wanted to hydrogenate a cholesterol or organic molecule, this kind of, they'd use Rainy nickel. And then in the report they'd say, and the catalyst was Rainy nickel. So his name appears in the literature more than anyone that's ever been involved in catalytic research. And as Murray Rainey, who was born in Kentucky and became famous the world over for his work. And he never allowed us how he knew anything about catalysis. And I think, again, that's one of the things that makes it a romantic subject. Well, I hope I got you interested enough tonight so that we continue on next time. Next time we'll talk about where catalysts are used today, the volumes of catalysts. I hope to have talk a little bit about a lot of the tools that we use. So when you walk in the laboratory and see these various tools, you'll better understand why we have them. And I may say a little bit about the involvement of several of these catalysts, the reforming catalysts and desulfurization catalysts. We would appreciate the week after that. I'm going to have 2 sessions in which I'm simply going to go through those pictures of all the processes that are used in the petroleum industry. And we're going to go through them fast. And my purpose in doing that is to familiarize you with the fact that all these processes have been devised to convert that barrel of crude into all these products. The best products, the most safe products, the most frugal products. And when someone tells you, well, there's nothing to it, you just